In the frozen depths of the outer solar system, 500 astronomical units from the Sun, far beyond the orbit of Neptune, something is very wrong. The orbits of dozens of distant rocky worlds out there seem to be tugged and twisted by an unseen hand. And according to our best models, the most likely explanation is a hidden planet silently circling the Sun on a vast, elongated orbit. This world could be up to 10 times the mass of Earth, and yet we can't find it. Astronomers have searched for this mysterious Planet 9 for more than a century, but every survey, every telescope sweep has come up empty. In an age where we can image planets orbiting stars dozens of light years away and glimpse the first galaxies born after the Big Bang, the fact that something this large could be hiding in our own solar system is deeply unsettling. But all this could be about to change. Earlier this year, scientists found something buried deep in the data from a 40-year-old space telescope. They've combined it with information from a newer dataset, and now, for the very first time, they may have an answer. Have scientists finally found Planet 9? I'm Alex McColgan, and you're watching Astrum. Join me today as we venture to the edge of our solar system in search of the missing Planet 9. We'll delve into the data these scientists are studying and find out what it takes to prove whether or not a planet exists. With new telescopes coming online, is it only a matter of time before our solar system has 9 planets once more? The outer reaches of the solar system is a mysterious place. Most unlike the inner region we inhabit. It's so distant that even if we set out at the speed of light, it would take more than 8 hours to get there. 9 billion kilometers is a long way. Upon arrival, we'd find darkness, peppered with unusual icy rocks, many of which we can barely detect, which we call trans-Neptunian objects or TNOs. The first TNO was discovered by Clyde Tombaugh in 1930. I suspect you've heard of it. It's called Pluto. However, it took another 60 years until we found the next TNO, and an age of discovery began. Today we've charted nearly 5,000 of these strange objects, but perhaps the most important find came in 2003, when a group of scientists led by Caltech's Professor Mike Brown decided to explore this outer realm. It wasn't long until they found Sedna, another dwarf planet less than half the size of Pluto, but with an inclined, highly elliptical orbit. This led to an explosion of interest in the outer solar system, as scientists rushed to explain why its orbit was so unusual. If it were just Sedna, it could be put down to chance. But with the increased attention came the discovery of many more TNOs with equally strange orbits. Some crossed the orbital path of Neptune, others moved in the opposite or retrograde direction to the 8 planets. Many were just greatly inclined. It raised the question, how did these orbits come to be? The only hypothesis that made sense of all of them is a 3-body interaction known as the Lidov-Kozai mechanism. It states that a near-circular but inclined prograde orbit can trade its inclination for eccentricity. But for that to happen requires 3 things: the Sun, the TNO, and a distant perturber. Mike Brown and his colleague Dr. Konstantin Batygin modeled the orbits of 17 TNOs and predicted that the chance of their movements being random was just 0.00006%. Instead, their model suggested that these objects were being perturbed by a mass they couldn't see, a planet-sized object to be exact. Enter Planet 9. Now, we can model all we like, but the only thing that can prove this is actual observation. As they say, seeing is believing. You'd think, given that Planet 9 is supposedly in our solar system, it should be pretty simple to point our telescope at where it should be and take a picture. But this is in fact exceptionally difficult to do. The brightness of a planet in the optical spectrum falls off at a rate inversely proportional to the fourth power of distance from the Sun, instead of the usual square of the distance, because for us to see it, the already diffused light has to reflect back. Previous optical wide field surveys from the Zwicky Transient Facility, the Dark Energy Survey and Pan-STARRS 1 have all spent years hunting, but none of them have found a single candidate for Planet 9. However, there is something else we can look for. All planets we know emit their own radiation in the infrared. A new team of planet hunters from Taiwan, led by Professor Tomo Goto and PhD student Terry Fan, decided to take advantage of this and look for Planet 9 in two far infrared all-sky surveys. The first taken by the Eris, or Infrared Astronomical Satellite, in 1983, and the second by the Akari Infrared Satellite, which is the Japanese word for light, in 2006. The Eris satellite conducted the first ever all-sky infrared survey above the obscuring warm blanket of Earth's atmosphere. Because of its vantage point and its ultra-cold sensor, cooled with superfluid helium to 2.5 degrees above absolute zero, it detected 350,000 new infrared sources, ranging from galaxies to asteroids. The Akari satellite was a similar design, but it had better spatial resolution and could record longer infrared wavelengths. The combined dataset of Eris and Akari was truly huge, with 2.4 million objects found across multiple decades. Filtering this for Planet 9 candidates was a mammoth task. Fan and Goto had to track each object's position individually. Their strategy was to compare the surveys across time, looking for objects that had moved in a way the models predicted Planet 9 would. They were looking specifically for a planet somewhere between 7 and 17 times the mass of Earth, with an orbital distance of around 280 astronomical units at its closest, or perihelion, and as far out as 1,120 astronomical units at its farthest, or aphelion. They also used that information to estimate the diameter of the planet and its black body temperature to narrow down their search further. Objects closer than around 500 astronomical units had already been searched by other groups, so Terry focused on the area between 500 and 700 astronomical units for his search. He then predicted what angular distance Planet 9 should cover in 23 years. He was hopeful. An object on a highly elliptical orbit moves much slower near its aphelion, so Planet 9 should spend more time out past 500 astronomical units and therefore be in the survey area for longer. Any data from these two satellites that did not fit that prediction was discounted, and incredibly, from over 2 million data points, Terry was left with only 13 candidates. From there, he painstakingly whittled those down by eye, and was left with just one. It's hard to tell, but in the top left corner of the Eris image, there are 7 pixels that are warmer than the background. And in the Akari image, taken 23 years later, the candidate has moved 47.5 arc minutes, the equivalent of 1.5 full moons, to the lower part of the image. Now, I think we can all agree that if we saw these images in isolation, we'd never guess what it is. But context is everything. We could be genuinely looking at the first image of Planet 9. Professor Goto says that if it is confirmed, he may allow Terry to finish his PhD early, which is probably fair enough. Much of the data surrounding this new candidate fits that expected of the proposed Planet 9, but there is some concern from Mike Brown and Konstantin Batygin about the inclination of the orbit of this new object being too steep. The team hasn't been able to completely map out how it moves, but Terry doesn't think we'll have to wait long to find out. The telescope set to follow up on these measurements is the Vera Rubin telescope. Featuring the largest camera sensor ever created at 3.2 gigapixels, it's able to capture objects that are orders of magnitude dimmer than previous optical sky surveys. And scientists believe it could increase the known objects in our solar system by up to a factor of 100. I recently made a video about the Vera Rubin Observatory, so if you want to find out more about it, then click this link. It's the best technology we have for the task. As Mike Brown says, if you were to hand me a big wad of cash and say, go build a telescope to go either find this Planet 9 or find the best evidence possible for Planet 9, I would probably go and build the Vera Rubin Observatory. The telescope's 10-year-long Legacy Survey of Space and Time, or LSST, is scanning the night sky to look for solar system objects, generating 20 terabytes of data in a single night. Give it a few years and we might know for sure if this is Planet 9. But in the meantime, Terry, Professor Goto, and their colleagues are not resting on their laurels. By filtering for the predicted parallax of Planet 9 in the Akari data, they have in fact already found 2 other possible candidates. One way or another, they are pretty sure that if Planet 9 is out there, they'll find it. Of course, not everyone is as confident. What if measurements show us it's not there? What then? Surprisingly to me, given the many orbital behaviors a theory needs to explain, there are several possible hypotheses. The first is of a new belt, a scaled-down version of what we see around a galactic center. 2/3 of spiral galaxies, including our own, are what's known as barred spiral galaxies, with a bar-like central region composed of millions of stars on aligned and highly elliptical orbits known as X1 orbits around the center of the galaxy and its supermassive black hole. These orbits emerge out of group dynamics, lots of small interactions, rather than one big one. Almost like a murmuration of birds, many tiny interactions between the individuals leads to coherent, beautiful movement without a conductor. In our solar system, we may find an equivalent, known as a Zederic-Madigan, or ZM belt, named after the 2 scientists who proposed it, Dr. Alexander Zederic and Dr. Anne-Marie Madigan. What we would expect to see around our sun if it had a ZM belt is what we see now, clustered elliptical orbits. And it's proposed that Sedna and other TNOs are actually part of that belt. In this hypothesis, a singular massive body like Planet 9 is not needed if the combined mass of the ZM belt is more than 10 to 20 Earths. Even better, the LSST program at the Vera Rubin Observatory will be able to detect if this belt exists or not. But there is a third explanation that will never be directly seen by any telescope. The cosmic equivalent of a hit and run that happened a very long time ago. The culprit here could have been another star passing through. The gravity of the object could have tugged on these outer bodies, disturbing their orbit enough and in such a way to cause the behavior we see today. But what if it wasn't a near miss? What if the object didn't escape? What if instead of a passing planet or star, our solar system captured a primordial black hole? That may sound implausible. However, it has been proposed that this is indeed not just possible, but around as likely as capturing a planet of equivalent mass. Primordial black holes are believed to have formed in the dense expansion phase of the Big Bang, and do not have a strict weight limit like those that are formed by a collapsing star. So one with the mass of a planet can exist, and would be about the size of a football. Impossible to see from Earth, unless, of course, it's consuming something. One final possibility is that we need to rewrite the laws of gravity. Proponents of modified Newtonian gravity, or MOND for short, claim that their model explains our current observations of the clustered TNO orbits. The increased pull from the galactic center under a MOND model is calculated to align the orbits towards it, and that's what we see. Now, there are issues with MOND, which I won't get into here, but it's curious that it could provide a good fit for the data for the TNOs in the solar system without needing a Planet 9. Planet, star, black hole, or a gravitational rewrite. What do you hope we'll find? Let me know in the comments. Personally, I hope it's a planet. For those of us who grew up and learned all about Pluto before it got downgraded, it would somehow be nice to go back up to 9 once more. And who doesn't want to complete our understanding of the solar system? Regardless of what it is, the Vera Rubin Observatory is now searching, and we're going to know for sure very soon. I can't wait to see what's out there. For more than 70 years, we thought our map of the solar system was complete. A familiar and tidy collection of 9 worlds orbiting a single star. But far out in the frozen darkness, billions of kilometers from the furthest known planet, a ghost was lurking. A tiny point of light, slowly, almost imperceptibly, drifting across astronomers' forgotten photographs, unnoticed and unknown for years. Its discovery wouldn't just add a 10th name to the roster of planets orbiting our Sun, it would trigger an identity crisis for the solar system itself, forcing astronomers into a bitter conflict over the meaning of one of the most fundamental words, and, in the process, redrawing our map of the solar system forever. This is the story of the world that, true to its name, sowed discord in the scientific community. I'm Alex McColgan, and you're watching Astrum. Join me today as we travel to the chaotic outer edges of our solar system to meet Eris, the world that started a war over the meaning of a single word: planet. The story of Eris begins not with a lucky glance through a telescope, but with a monumental effort to take an inventory of the Sun's most distant subjects. At the Palomar Observatory in California, a team of astronomers, Mike Brown, Chad Trujillo, and David Rabinovitz, had embarked on a systematic survey of the outer reaches of our solar system, looking for signs of objects orbiting beyond Neptune, dubbed trans-Neptunian objects, or TNOs. The team were using the 1.2 meter Samuel Oschin telescope to capture images of a wide field of the sky, putting them through automated image searching software that flagged objects moving at a certain speed, and their search had already proved fruitful. With newly discovered worlds like Quawa, Orcus, and Sedna, they were gradually populating this dark, distant realm, but the team were hoping to find something bigger. As Mike Brown later wrote, there had to be a 10th planet. The possibility that Pluto was a unique planetary oddball out at the edge of the solar system seemed absurd to me. He decided to manually re-examine some old datasets that his software had passed over. Then, after months of rechecking, on the 5th of January 2005, Brown began clicking through a sequence of 3 images from the 21st of October 2003, and there in the images was a single, faint dot of light, moving at a glacial pace against the background of fixed stars. Brown knew instantly that this was something significant. It was bright, meaning it was either large or highly reflective, and it was moving far slower than anything they had found before, meaning it was incredibly far away. His first thought was, "I found a planet." The team began tracking the object, provisionally designated 2003 UB313, to determine its orbit and size. They had planned to keep their discovery under wraps until they had completed further observations, but the competitive world of planetary science intervened. On the 27th of July 2005, a different team controversially announced the discovery of another large TNO, Haumea, after accessing Brown's team's public observation logs. To avoid being scooped again, Brown's team was forced to go public. On the 29th of July, they announced the discovery of not just one, but two major bodies in the outer solar system, Haumea and this new object that would eventually become known as Eris. The secret was out, and the solar system would never be the same. In Greek mythology, Eris is the goddess of strife, a malevolent deity who, when snubbed from a wedding, tossed a golden apple inscribed "For the fairest" among the goddesses, instigating a quarrel that led directly to the Trojan War. In 2005, the discovery of the celestial body that would bear her name was the modern equivalent of that golden apple, thrown into the halls of astronomy. It ignited a scientific war over the very definition of a planet. The problem was simple, yet profound. Initial estimates suggested Eris was larger than Pluto, and subsequent calculations based on its moon's orbit showed it was 27% more massive. If Pluto was a planet, then Eris, its more massive twin, certainly had to be one as well. And if Eris was a planet, what about the other large TNOs that had recently been discovered, such as Makemake, Haumea, and Sedna? Where would the line be drawn? The discovery created an unavoidable logical crisis. As Mike Brown put it, we were either going to have to add new planets or subtract one. The International Astronomical Union, the global body responsible for astronomical nomenclature, was forced to act. At its 26th General Assembly in Prague in August 2006, the question of what is a planet was put to a formal debate and vote for the first time in history. The debate was vigorous and exposed a deep rift within the astronomical community, splitting it into two main camps. On one side were those who advocated for a geophysical definition. They argued that a planet should be defined by its intrinsic properties. If an object is massive enough for its own gravity to overcome its material strength and pull it into a nearly round shape, a state known as hydrostatic equilibrium, it should be called a planet. Under this simple definition, Pluto, Eris, the dwarf planet Ceres, and potentially dozens of other bodies would have become planets. On the other side were those who favored a dynamical definition. They argued that a planet's identity is tied not just to its physical state, but to its gravitational influence on its surroundings. A true planet, they contended, must be the dominant gravitational player in its orbital zone. In the words of the final resolution, it must have cleared the neighborhood around its orbit. The voting process itself was fraught with controversy. The final vote was held on the last day of the 10-day conference, by which time most of the 2,500 attendees had already gone home. Only 424 astronomers were present to cast their ballots, a tiny fraction of the global astronomical community. When the votes were counted, the dynamical definition had won. The IAU passed Resolution 5A, establishing a three-part definition for a planet in the solar system. It must A. be in orbit around the Sun, B. be in hydrostatic equilibrium, and C. have cleared its neighborhood. Pluto, sharing its orbital space with Neptune and a host of other Kuiper Belt objects, failed on the third criterion. A new category was created, the dwarf planet, for objects that meet the first two criteria, but not the third. Crucially, a follow-up resolution was defeated that would have made dwarf planet a subcategory of planet. Instead, the IAU declared that planets and dwarf planets are two distinct classes of objects. In an instant, the solar system was officially reduced to just 8 planets. Critics immediately pointed out flaws in this definition. The phrase "cleared the neighborhood" was ambiguous, and the first criterion, in orbit around the Sun, applied only to our solar system and ignored the thousands of exoplanets that we now know exist. It was not a universal, elegant principle, but a reactive, controversial, and local fix. With the debate settled, at least officially, the Discovery team had the honor of naming their troublemaking world They chose Eris, a name Mike Brown felt was perfect for the object that had thrown astronomy into such strife. The name was formally accepted in September 2006, cementing the legacy of this distant world as the celestial apple of discord. Having established its role as a cosmic disruptor, it's time to journey to Eris itself and understand the nature of this renegade world. Eris does not reside in the relatively stable, disk-like Kuiper Belt, the home of Pluto and many other icy bodies. Instead, it belongs to a far more chaotic and wild region known as the Scattered Disk. The Scattered Disk is a vast, sparsely populated halo of icy objects with extreme orbits. These are the solar system's outcasts, bodies that likely formed closer to the Sun but were gravitationally scattered into their current paths by Neptune as it migrated into its current orbit billions of years ago. Eris's orbit isn't a circle like you might expect, but a huge ellipse that takes it 557 Earth years to trace. At its closest approach, or perihelion, Eris comes within about 38 astronomical units of the Sun, roughly the same distance as Pluto's average orbit. But at its furthest point, or aphelion, it swings out nearly 98 astronomical units, almost 15 billion kilometers away. That's nearly 3 times Pluto's current distance from the Sun. Eris's orbit is also steeply inclined at 44 degrees to the ecliptic, the plane on which the main planets travel. This means Eris spends its 557 Earth-year-long year soaring high above and plunging far below the rest of the solar system. For years, Eris was thought to be Pluto's larger twin, but in 2010, astronomers had a chance to measure it with incredible precision. Eris passed directly in front of a distant star, an event known as a stellar occultation. By timing how long the star's light was blocked from different locations on Earth, they could calculate its size with pinpoint accuracy. The result was a surprise. With a diameter of 2,326 kilometers, Eris was almost exactly the same size as Pluto, and in fact, slightly smaller. This revealed the most crucial difference between the two worlds. With a mass 27% greater than Pluto's packed into a slightly smaller volume, Eris must be significantly denser. Scientists calculated its density at 2.43 grams per cubic centimeter, substantially higher than Pluto's 1.85 grams per cubic centimeter. This points to a very different internal structure. While Pluto is thought to be a roughly 70-30% mix of rock and ice, Eris must be composed predominantly of rock, with only a comparatively thin mantle of ice on top, a rocky heart in a frozen shell. That shell is also one of the most brilliant surfaces in the solar system. Eris has an incredibly high albedo of 0.99, meaning it reflects 99% of the sunlight that reaches it. This dazzling brightness is potentially due to a phenomenon called atmospheric collapse. Like Pluto, Eris has an atmosphere, primarily composed of nitrogen and methane ice that is turned to gas. But as its extreme orbit carries it into the deep freeze of its aphelion, this atmosphere freezes solid and falls to the surface as a fresh, bright layer of frost or snow. As Eris begins its 280-year journey back towards the Sun, this frost will warm and sublimate, turning back into a gas and renewing the atmosphere, only to freeze and fall again centuries later. And more recently, observations from the James Webb Space Telescope have added another layer of complexity. Analysis of different isotopes of methane on Eris's surface suggests they may have been produced by geothermal activity, hinting at unexpected thermal processes deep within its rocky core. This distant, frozen world may have, or at least once had, a warm heart. The key to unlocking Eris's secrets, and the final piece of evidence that would seal Pluto's fate, came in September 2005. Using the Advanced Adaptive Optics System on the WM Keck telescope, a telescope that corrects for the blurring effects of Earth's atmosphere to produce space telescope quality images, Mike Brown and his team spotted a faint companion orbiting Eris. It had a moon. This changed everything. While an object's size can be estimated from its brightness, its mass can only be determined with certainty by observing its gravitational pull on another body, for instance, a natural satellite. By carefully tracking the moon's nearly circular 16-day orbit, the team could apply Kepler's law of planetary motion to calculate the mass of Eris with great precision. It was this calculation that definitively proved Eris was more massive than Pluto, making the planet debate not just an academic exercise, but an urgent necessity. The moon itself is a stark contrast to its parent. While only 25% the diameter of Eris, this moon is one of the largest of any dwarf planet, second only to Pluto's own Charon, and larger than Saturn's Enceladus or Mimas. It's also tidally locked to Eris, but estimates of its mass from how much it causes Eris to wobble in its position are far below what would usually allow tidal locking. This suggests that Eris itself dissipates energy far more easily than we first thought. While Eris is brilliant white, its moon is incredibly dark, described as being darker than coal. This suggests a very different surface composition, devoid of the bright frosts that coat Eris. The leading hypothesis for the moon's origin is a giant impact, much like the one that formed Earth's moon. Early in the solar system's history, a massive object likely slammed into the young Eris, blasting a cloud of debris into orbit that eventually coalesced to form a single satellite. This violent birth would have stripped away volatile ices, leaving behind a darker, rockier body. Just as Eris was named for the goddess of discord, her moon was given the name of her mythological daughter, Dysnomia, the demon spirit of lawlessness. The name is fitting for a moon born from chaos, orbiting a world that overturned the established laws of the solar system. In the years since the 2006 vote, Mike Brown has earned the name the Pluto Killer. But this misses the true legacy of his discovery. Finding Eris didn't kill Pluto, it revealed Pluto's true family, making our solar system larger, more complex, and more interesting. For decades, we had a flawed model, 8 planets of a certain character, and then one strange outlier. By forcing this reclassification, Eris gave us a more accurate and coherent picture of our cosmic home. There are 4 inner rocky terrestrial planets. There are 4 gas and ice giants. And beyond them lies a vast third realm, a swarm of thousands of icy dwarf planets, a population of worlds whose existence we were only just beginning to grasp. Eris and Pluto are kings of this third zone, the largest and most prominent members of the trans-Neptunian population discovered so far. And Eris itself remains the ultimate mystery. It is the most massive known object in our solar system that has not been yet visited by a spacecraft. While NASA's New Horizons mission gave us a breathtaking, intimate portrait of Pluto, Eris remains a distant point of light, its secrets held across billions of kilometers of empty space. A proposed flyby mission would take an estimated 25 years just to reach its destination, a journey that would span generations. For the foreseeable future, the goddess of discord will keep her secrets. Her discovery resolved one great debate, but it opened up a new chapter in our exploration of the solar system, reminding us that the most exciting discoveries are not those that provide the final answers, but those that reveal just how much more there is left to explore. In the summer of 1977, NASA's Jet Propulsion Laboratory launched a pair of Titan Centaur rockets containing nearly identical spacecraft. Known as Voyager 1 and Voyager 2, these twin probes were built to last for 5 years with the intention of studying Jupiter and Saturn and their larger moons. Incredibly, nearly 45 years later, NASA is still in constant communication with both probes, which take routine commands and transmit data back to Earth's deep space network, making Voyager the longest running mission in the history of space exploration. After completing all of its initial objectives within 4 years, NASA extended Voyager's mission to include the two outer giants, Neptune and Uranus, before embarking on the even more ambitious Voyager interstellar mission, with the purpose of exploring the outer limits of the Sun's sphere of influence and beyond. Voyager 1 and 2 have now travelled 22 billion kilometers and 18 billion kilometers from Earth, respectively. So far, they have left the heliosphere and entered interstellar space. But time, even for the long-lived Voyager probes, is running out. Perhaps as soon as 2025, the probes will lose their remaining power supply and go dark forever. In preparation for this, NASA has begun taking the probe's instruments offline, in the hope of extending the life of the mission for a few more years. But when the Voyager probes inevitably go dark, they will leave behind a wealth of data that is unprecedented in its size and scope. So now that we are entering the Voyager mission's final days, we can ask, what did Voyagers 1 and 2 discover out there? Did the probes and their instruments hold up under the rigors of interstellar travel? And why are scientists so surprised by what they learned? I'm Alex McColgan and you're watching Astrum. Join me today as we look at the most stunning discoveries of the nearly 45-year Voyager mission and relive the remarkable journey the probes took after they left Neptune's orbit, traveling from the solar system's icy outer giants to the brink of interstellar space. While Voyagers 1 and 2 were supposed to be on a 5-year mission, their team of forward-thinking scientists and engineers made a number of design choices that enabled the probes to hold up over a much longer journey. Each probe is equipped with a long-lasting radioisotope thermoelectric generator, which converts heat from the decaying plutonium-238 isotope into electric power. These probes also have redundancies of most of their 11 scientific instruments in case of machine failure, as well as 16 hydrazine thrusters, including 8 backups. Most importantly, the launch happened at the perfect time. When the Voyager planetary mission launched in 1977, NASA took advantage of a once-in-176-year alignment of the planets, which not only allowed for flybys of Neptune and Uranus with minimal course adjustment, but gave the probes a gravity assist from each of the giants they visited, thereby increasing their effective velocity beyond what they could get from their own rocket propulsion. This idea was relatively new at the time, having been only attempted previously on NASA's Pioneer missions to Jupiter and Saturn. In 1981, Voyager 1 escaped the ecliptic, which is the Earth's plane of orbit around the Sun, heading 35 degrees to the north. Voyager 2 later went under the ecliptic, heading 48 degrees to the south. After the Voyager planetary mission was extended to become the Voyager interstellar mission, the cameras on both probes were deactivated in order to conserve power. The last image taken by Voyager 1 is the famous pale blue dot photograph of Earth, taken from a distance of around 6 billion kilometers, the most remote image of Earth ever taken. However, this was barely the start of the Voyager's journeys. To reach interstellar space, the probes would have to traverse the termination shock, a region in which hypersonic solar winds run into fierce resistance from the interstellar wind. Beyond the termination shock, the Voyagers would encounter the heliosheath, where slowing solar winds pile up, becoming denser and hotter, followed by the heliopause, the final boundary between the heliosphere and interstellar space. But in spite of what you may think, the start of the interstellar medium doesn't actually mark the end of our solar system. Indeed, it will be another 300 years until Voyager 1 reaches the Oort Cloud, the vast region of billions of icy planetesimals that surround our solar system like a bubble, and another 30,000 years until it exits the cloud, leaving our solar system forever. When the Voyagers travelled through the heliosheath, they made an incredible discovery. Because the Sun's magnetic field spins in opposite directions on its north and south poles, the spin creates a ripple where they meet called the heliospheric current sheet, sort of like the rings created by dropping a stone in water. However, when this sheet reaches the termination shock, it compresses, as though the ripples were hitting the edge of a pool. The Voyager probes discovered that after the termination shock, these stacked up ripples form magnetic bubbles. This means the boundary of the heliosheath is not as smooth and clear-cut as scientists thought. Instead, it is a fluctuating and magnetically bubbly environment. This messy finding has prompted a complete revision of our model of the heliosheath. On the 25th of July 2012, the Voyager 1 space probe became the first man-made object to leave the Sun's heliosphere and enter interstellar space. It was traveling at an incredible speed of 540 million kilometers per year, or 3.6 astronomical units, an astronomical unit being the distance between Earth and the Sun. The distance at which Voyager 1 crossed the heliopause was about 120 astronomical units from the Sun, which itself was a revelation. It was unknown where, exactly, the heliopause occurred. Funnily enough, some early models put it as close as Jupiter, and others much further. Remember, the heliopause is the boundary where the Sun's solar wind is stopped by its collision with the interstellar medium, kind of like the crashing of two powerful bodies of water against each other. Solar wind is the steady stream of charged particles, such as electrons, protons, and alpha particles, that come from the Sun's outer layer. The interstellar medium, by contrast, consists of charged particles, gases, and cosmic dust left over from the Big Bang and other ancient supernovae. When these charged streams hit each other, they change course and form a region of equilibrium called the heliopause boundary. At first, NASA wasn't sure if Voyager 1 had truly crossed the heliopause and entered interstellar space. As models predicted, the probe's plasma wave detector found a massive increase in plasma density, 80 times what it had registered in the outer heliosheath, and a spike in galactic cosmic rays. But something strange didn't happen that left scientists baffled. After crossing the heliopause, Voyager 1 detected no change in the ambient magnetic field. Why was that so surprising? Well, theoretical models assumed that the ambient magnetic orientation would change in a region dominated by the magnetic fields of other stars. But remarkably, Voyager 1 detected no discernible change in the ambient magnetism. NASA was so confused that they waited nearly a year before announcing that Voyager 1 had, in fact, entered interstellar space. On the 5th of November 2018, Voyager 2, traveling at the slightly slower speed of 490 million kilometers, or 3.3 astronomical units per year, joined Voyager 1 in becoming the second man-made object to enter interstellar space. The crossing also occurred 120 astronomical units from the Sun, and like the Voyager 1 6 years earlier, the probe detected no change in the ambient magnetic field. But something else surprised scientists. You see, the Sun goes through 11-year solar cycles, during which its activity waxes and wanes. Voyager 2's crossing occurred at a time when solar winds were peaking. Models predicted that the size of the heliosphere would fluctuate with the solar cycle, meaning it would have been expanding when Voyager 2 made its crossing. Yet, Voyager 2 crossed the heliopause at exactly the same distance Voyager 1 had 6 years prior, meaning our models were wrong. Like the magnetometer finding, this demonstrated the value of testing theoretical models with field data. We now suspect the boundary between the heliosphere and interstellar medium is much more twisted and filled with fluctuations than prior models proposed. One leading idea is that our Sun emerged billions of years ago from a hot and heavily ionized region following the explosion of one or more supernovae, and that magnetic turbulence persists to this day near the heliopause. If so, the probes will likely encounter a different magnetic orientation as they travel further away, but their instruments will probably be long dark by that time. Although the historic Voyager mission will soon be ending, the twin probes are just beginning their cosmic journeys. In 40,000 years, Voyager 1 will likely drift towards a star in the Camelopardalis constellation, while Voyager 2 will pass 1.7 light-years from the star Ross 248. In 296,000 years, it will pass 4.3 light-years from Sirius. These small, intrepid probes will likely outlast the Earth itself as they continue their solitary wanderings across the Milky Way. And if by chance they encounter intelligent life in one of the far reaches of our galaxy, they will be a testament to mankind's ingenuity and resilience. On each of the probes is a golden audiovisual disc called the Golden Record. These records carry photographs of Earth and its many life forms, the sounds of whales and of babies crying, music by Mozart and Chuck Berry, and dozens of indigenous peoples and greetings in 55 languages. They would offer a distant stranger a glimpse of who we are and what life on Earth is like. As for us, we must say goodbye to these old familiar friends and continue our own lives here on Earth. Hopefully the Voyager mission will not be our last brush with the stars, but only the beginning. In the dark, frigid void beyond Neptune lies a vast and mysterious region where the ancient remnants of our solar system's birth drift silently through the darkness, perfectly preserved by the deep freeze of space. To reach this shadowy expanse from Earth, we must travel past the rocky planets, flying by Mars and then beyond the swirling storms of Jupiter and Saturn. Farther still, out beyond the blue giants, Uranus and Neptune, we finally reach our destination. Welcome to the Kuiper Belt, a vast ring of icy debris encircling our solar system like a frozen halo. This isn't just a collection of distant rocks, it's a time capsule from 4.6 billion years ago, holding the untouched building blocks of our cosmic neighborhood. It is home to several dwarf planets and mysterious objects that have left many astronomers scratching their heads. I'm Alex McColgan and you're watching Astrum. Join me today as we explore the worlds lurking in the shadows of our solar system and piece together clues about its history, about planetary formation, comet activity, and even the origins of life. Before we knew for sure that the Kuiper Belt was real, astronomers suspected that something existed beyond Neptune. For decades, everyone's favorite dwarf planet, Pluto, was thought to be an isolated object in the outer solar system, but something didn't add up. Its small size and unusual orbit suggested that Pluto wasn't alone, and that maybe it was merely one of a number of yet-to-be discovered distant objects. In 1951, astronomer Gerhard Kuiper predicted the existence of a belt of icy objects just beyond the orbit of Neptune, but without telescopes powerful enough to detect these objects, the idea remained theoretical for decades. That changed in 1992, when astronomers David Jewitt and Jane Liu discovered the first confirmed Kuiper Belt object, known as 1992 QB1. Pluto and its moon Charon were both discovered before 1992 QB1, Pluto in 1930 and Charon in 1978, but these objects were only confirmed as KBOs after the 1992 KBO. Since then, thousands more Kuiper Belt objects have been identified, populating this distant region beyond Neptune. To grasp the true scale and position of the Kuiper Belt, let's imagine we're traveling in a spaceship, starting from the Sun and moving out towards the outer edge of our solar system. As we move along our journey, let's compare the Kuiper Belt to both the more well-known asteroid belt and the less well-known Oort Cloud. Starting near the Sun, we zip past the rocky planets, Mercury, Venus, Earth, and Mars. Between Mars and Jupiter, we see the asteroid belt, made up of the leftover materials from when our planets formed. A thin, spread out ring of rocky debris, the asteroid belt is about 2.2 to 3.2 astronomical units away from the Sun and about 1 astronomical unit wide. As a reminder, 1 astronomical unit is equivalent to the distance from the Sun to the Earth. Most of the known asteroids reside in this part of our solar system, ranging in size from the largest asteroid, Vesta, at 525 kilometers wide, almost the distance from London to Belfast, to the smallest objects, some of which are just tens of kilometers across. However, despite residing in such a large space, the total mass of all of the asteroids in the whole asteroid belt combined is only about 3% of the mass of the Moon. Beyond the asteroid belt, we encounter the gas and ice giants, Jupiter, Saturn, Uranus and Neptune, colossal worlds that dominate the outer solar system. Finally, as we pass Neptune's orbit at 30 astronomical units, we reach our destination, an even more remote, icy frontier, the Kuiper Belt. This vast expanse stretches from 30 to 50 astronomical units and is home to a range of intriguing objects, from frozen relics of the early solar system to dwarf planets including Pluto, Haumea, Eris, Makemake, and countless other smaller objects. Like the asteroid belt, the Kuiper Belt contains ancient debris from our early solar system. In fact, Kuiper Belt objects are considered some of the oldest surviving pieces of our solar nebula that originally formed the planets of our solar system. And so, at one point in the very distant past, these stray pieces might have been able to come together to form yet another planetary body. However, Neptune's gravity prevented the icy objects from coalescing and never allowed them to form something new. Unlike the asteroid belt, which is primarily made of rocky material, the Kuiper Belt consists of mostly frozen methane, ammonia, and water ice, forming a frozen, thick, donut-shaped ring of debris. The Kuiper Belt contains hundreds of thousands of large icy bodies bigger than 100 kilometers across, and more than 1 trillion comets, not to mention smaller debris and dust. And the average distance between objects is so large it can be hard to imagine. Each of those objects is, on average, between 0.02 to 0.1 astronomical unit apart. Imagine 10 million kilometers between objects. Here, in the dim outer reaches of our solar system, these icy bodies drift in near silence, preserving vital clues about the origins of planets and comets. But it doesn't end there. That was just the main region of the Kuiper Belt. Overlapping the outer edge of the main region is another area of Kuiper Belt called the scattered disk, which continues out to nearly 1,000 astronomical units, with some Kuiper Belt objects on orbits that reach even farther beyond that. So while the asteroid belt and Kuiper Belt share some similarities, as you can see, one is vastly more expansive than the other. And while we may have reached the end of the Kuiper Belt, there's still another massive structure that surrounds every other object and belt I've mentioned so far. In a recent video, I talked about the Oort Cloud, the colossal structure of orbiting icy debris that encircles our entire solar system. It's so jaw-droppingly far away that even our most powerful telescopes can't catch a glimpse. So how do those two structures, the Oort Cloud and the Kuiper Belt, differ from each other? For one, the Kuiper Belt is thousands of times closer to the Sun than the center of the Oort Cloud, which is theorized to stretch from 2,000 to 100,000 astronomical units. Another major difference is that the Kuiper Belt is donut-shaped, while the Oort Cloud is spherical, like a gigantic bubble of swarming debris. But something these structures do have in common is that they are both sources of the celestial phenomenon that we know as comets. The Oort Cloud is the source of many long-period comets, while the Kuiper Belt is where some short-period comets are born. While the Kuiper Belt today is one of the most massive structures in the solar system, it's just a small fraction of what it once was. Originally, altogether, it probably contained 7 to 10 times the mass of Earth, but the shifting orbits of the 4 giant gas and ice planets caused most of that to be lost to space. What remains is no more than about 10% of Earth's mass. Not only that, but the Kuiper Belt today continues to slowly erode away. As objects occasionally collide and break apart, smaller fragments are left in their wake, and some of the resulting dust is blown out of the solar system by the solar wind. Sometimes these collisions, or Neptune's gravity, will cause Kuiper Belt objects to head on a new path towards the Sun, creating short-period comets which have orbits of less than 200 years. Over time, the Sun's radiation causes comets to shed material, producing the spectacular tails we see from Earth. Several famous comets originate from the Kuiper Belt, or its scattered disk, including Halley's Comet, with an average orbital period of 76 Earth years, or Comet Shoemaker-Levy 9, which broke apart and smashed into Jupiter in 1994 in the first ever observed collision of 2 solar system bodies. As we all know, Jupiter survived, but the impact was visible from Earth and was quite a spectacular sight to behold. You can see it out for yourself if you check out my video on the aftermath of this collision. You may also have heard in the news recently about a near-Earth asteroid named 2024 YR4. While there is a very small chance of this asteroid colliding with our moon, or even a smaller chance of it impacting Earth, the short-period comets originating from the Kuiper Belt pose no immediate threat to us in the next 100 or more years. In other words, you don't need to worry about that. Despite the Kuiper Belt being just a small remnant of what it once was, it still offers a nearly endless frontier of objects for us to explore. And unlike the Oort Cloud, which we have not been able to visit yet, we have been to the Kuiper Belt. While most of what we know about the Kuiper Belt comes from ground-based telescopes and the Hubble Space Telescope, NASA's New Horizons is the only spacecraft to have actually been there. It performed a flyby of the dwarf planet Pluto and Kuiper Belt object 2014 MU69, which was later officially named Arakoth, meaning sky, in the Native American Powhatan or Algonquian language. This flyby of Arakoth in 2019 was the most distant flyby in the history of space exploration, taking place 1.5 billion kilometers beyond Pluto, with the New Horizons spacecraft getting as close as about 3,500 kilometers above the surface of the object. And even among the swarm of mysterious objects that make up the Kuiper Belt, Arakoth still managed to surprise the New Horizons team. Its strange shape was unlike anything we had ever seen in our solar system. Arakoth is a small icy KBO known as a contact binary, composed of 2 distinct lobes that at some point merged into one body. Its shape resembles a flattened snowman. At just 35 kilometers long, 20 kilometers wide, and 10 kilometers thick, you might not think there's much to learn from this relatively tiny object. But what Arakoth lacked in atmosphere and diverse geology, it made up for in its unique structure. The bizarre pancake snowman shape of this Kuiper Belt object provides crucial insights into how planetary building blocks came together in the early solar system, and how planets may have formed. Arakoth's shape seemed to give it a counterintuitive gravity field and rotation, and several papers published since the flyby have led to an almost undeniable truth about how planetesimals form, something the New Horizons team didn't expect. Planetesimals form when smaller objects come together to make larger bodies, which may eventually combine to create a planet. Until now, there have been 2 competing theories: hierarchical accretion, which proposed that small objects would crash into each other at high speeds until they created something bigger, and local cloud collapse, where nearby objects would slowly come together because of their gravitational attraction, thereby forming larger and larger bodies. And now, thanks to the Arakoth flyby and important research into the object's geology, geophysics, composition and formation, we can be fairly certain that the theory of local cloud collapse is correct. The object's smooth surface and the lack of fractures from stress confirm that the cosmic snowman formed at low speed. Alan Stern, a planetary scientist and the lead for the New Horizons mission, said that the evidence was so strong, we've decisively solved a multi-decade debate about how planetesimals form. And thanks to New Horizons, we get to see the most famous Kuiper Belt object, Pluto. The spacecraft performed a flyby in 2015, allowing us to get up close and personal like never before and take those stunning images. The mission collected observations of Pluto and Charon, the dwarf planet's largest moon, and was able to collect data on Pluto's other satellites, Nix, Hydra, Kerberos, and Styx. Of course, we've all seen the stunning photographs of Pluto's heart-shaped surface region, also known as Tomba Regio. But did you know that the heart-shaped feature is actually a glacier? The western lobe of the heart, named Sputnik Planitia, after Earth's first artificial satellite, Sputnik 1, is a vast nitrogen glacier that stretches 1,000 kilometers wide and 4 kilometers deep, and is undoubtedly the largest known glacier in the solar system. The eastern lobe of the heart gets its light color from nitrogen that is carried from Sputnik Planitia and deposited as ice. Not only did we get stunning images of Pluto, but the data from New Horizons forever changed how we understand our favorite dwarf planet. It revealed that Pluto is far more complex than we previously thought, and offered clues to the origin of its heart-shaped feature. The data led some to believe that Pluto's heart-shaped region could be explained by an internal water-ice ocean. However, a recent study led by astrophysicist Harry Ballantyne from the University of Bern has revealed another, more likely culprit. The heart shape may have been caused by a low-velocity impact that left a gigantic splatter across the surface of Pluto, creating the western half of the heart shape. This impact would have come in at an oblique angle, as in not straight on. Imagine throwing a water balloon across dry pavement in the same way you might skip a stone across a pond. When the balloon scrapes the pavement, it pops, leaving an elongated splat of water across the pavement. This kind of angled, low-velocity impact is similar to how the western lobe of Pluto's heart feature may have been created. But it's not just Pluto that we get to see up close. The images of Pluto's moon Charon were also incredible. Can you make out the enormous equatorial tectonic belt? Its existence suggests a long-gone water-ice ocean on Charon. So what comes next in our quest to understand the Kuiper Belt and, consequently, to understand our solar system? New Horizons is expected to exit the Kuiper Belt sometime between 2028 and 2029. And while there is no current target for a further flyby, it is possible that NASA identifies another suitable target. New tools like the James Webb Space Telescope could help us to further analyze the composition of Kuiper Belt objects. And perhaps in the distant future, a robotic mission might allow us to land on one of these mysterious objects, or even collect a sample for a return mission back to Earth. Who knows what else we'll discover out there in this vast frozen frontier. As technology advances, future missions will hopefully push deeper into the Kuiper Belt, revealing more of its long-held secrets, one icy world at a time. What if I told you that there is a colossal structure that begins at the edge of our solar system? One that encircles our sun and all of the planets, but we've never seen it. A shell made up of billions or even trillions of ancient icy chunks the size of mountains marks the outermost boundary of our solar system, or so we think. Jaw-droppingly far away, beyond the reach of even our most powerful telescopes, the Oort Cloud is a region shrouded in mystery and speculation where the sun's influence grows faint as it brushes up against the void of interstellar space. What exactly is this Oort Cloud? If we've never directly observed it, how do we know it's out there? And why do some people question its existence? Let's find out. I'm Alex McColgan and you're watching Astrum. Join me today as we venture to the farthest reaches of our solar system and beyond to construct an image of this unseen astronomical wonder. You've probably heard of the asteroid belt and maybe even the Kuiper Belt. At two different locations in our solar system, these roughly donut-shaped bands of debris each move in the same direction and more or less on the same orbital plane as the planets around our Sun. The asteroid belt is the closest to the Sun of these two debris rings, located between Mars and Jupiter, and consists of millions of orbiting asteroids. The Kuiper Belt, on the other hand, was first proposed by astronomer Gerard Kuiper as the origin of short-period comets in the mid-20th century. It is a massive field of icy debris out past Neptune. Occasionally, a piece of Kuiper Belt debris will get pushed by gravity, sending it on a new orbit closer to the Sun. In some cases, this creates a new short-period comet. These comets have orbits of less than 200 years and are often predictable as they continue to make subsequent orbits around the Sun. At the same time that Kuiper was investigating short-period comets, a Dutch astronomer named Jan Oort was contemplating the origin of long-period comets. Few scientists of the 20th century made more contributions to astronomy than Oort. In 1927, he calculated our place in the Milky Way galaxy, and in 1932, he was the first to find evidence of dark matter, to name a few examples of his discoveries. In 1950, Oort was the first to theorize the existence of a thick bubble of swarming, icy debris that surrounded our entire solar system, now known as the Oort Cloud. But unlike the asteroid belt and Kuiper Belt, it's still yet to be directly observed. To understand this theory, let me explain what led Oort to this proposition. Unlike comets with short orbits, such as Halley's Comet with an average period of 75.3 years, or Comet Encke with a period of just 3.3 years, long-period comets were unpredictable. For one thing, their orbital periods were so long that in some cases they could take as many as 30 million years to complete one orbit. And curiously, these comets came from all different directions and had various orbital inclinations. It was a mystery on the grandest of scales, but Oort noticed a few things that all of these long-period comets had in common. Their orbits indicated that these comets weren't coming from far out in interstellar space, but that their origin had to be closer to home. However, as I'll explain in a moment, not too close to home. So, if these long-period comets weren't coming from the Kuiper Belt and weren't coming from far out in interstellar space, where were they coming from? Oort found a peculiar similarity among the orbits of these comets, one that might provide the answer to that question. The point in a comet's orbit where it is most distant from the Sun is called the aphelion. Oort noticed that all observed long-period comets seem to have an aphelion that all grouped around a certain distance, around 7.5 trillion kilometers from the Sun. That's right, trillion with a T. As you can see, when it comes to the distances I'll be talking about in this video, our typical units of measurement fall a bit short. So instead of using kilometers, I will switch to astronomical units. One astronomical unit, or AU, is defined as the distance between Earth and the Sun, or about 150 million kilometers. So Earth is 1 AU from the Sun. The aphelia grouping that Oort noticed, where the long-period comets reached their farthest orbital distance from the Sun, was about 50,000 astronomical units. To help picture the orbits of these long-period comets, Keep in mind that the outermost planet in our solar system, Neptune, is around 30 AU from the Sun, or about 4.5 billion kilometers. The main region of the Kuiper Belt extends from Neptune's orbit at 30 AU out to around 50 AU, but recent evidence from NASA's New Horizons spacecraft suggests a second region of the Kuiper Belt called the Scattered Disk, which continues to around 1000 AU. It's with these key findings from observed comets that they didn't come from far out in interstellar space, the orbital distances clustered around 50,000 AU, and the fact that they arrived from any direction and orbital inclination, that Oort theorized a special spherical swarm of icy debris that he believed to be the origin of long-period comets. In the years since then, mathematical models have shown agreement with the Oort Cloud theory, and astronomers have further theorized various mechanics by which the Oort Cloud came to be in its current state. The leading idea is that the Oort Cloud formed from ancient debris, leftovers from when our planet formed 4.6 billion years ago. After the planets formed, the surrounding area was still rich with these smaller, leftover chunks of material called planetesimals. The gravity from these early planets then scattered the leftover material in every direction. Some material was flung out of the solar system entirely, but a significant portion was sent into seemingly random, eccentric orbits around the Sun. These scattered planetesimals had eccentric enough orbits that they were influenced by gravitational forces outside of our solar system, while still remaining captured in our Sun's orbit. And it's believed that this is how these billions or trillions of icy chunks came to be part of the Oort Cloud. Gravitational perturbations can force Kuiper Belt objects out of place, creating short-period comets. We think that similar forces are what send Oort Cloud objects into elliptical orbits with the Sun, thereby creating long-period comets. These perturbations could be caused by passing stars or molecular clouds or tidal forces from the Milky Way itself. In fact, about 70,000 years ago, Schultz's star gained the title of the star that came closest to our solar system, actually grazing the outer region of the Oort Cloud. But luckily for us, it didn't cause any catastrophic disruptions to the Oort Cloud or our solar system at large. Schultz's star is a low-mass binary system made up of a red dwarf and a brown dwarf companion. So 10 millennia ago, even at a much closer distance to the Oort Cloud, the gravitational influence of this binary star was significantly weaker than that of our much more massive Sun. However, while most objects experience little to no impact during the low-mass star's brief encounter with the edge of the Oort Cloud, numerical simulations from 2018 concluded that Schultz's star is believed to have nudged at least some objects out of place, creating and influencing the trajectory of some long-period comets. But the Sun has been around for over 4 billion years, and that's a lot of time for other close encounters with stars in the distant past. Could these interactions have prevented the Oort Cloud from forming? Our models suggest no. However, Oort Cloud material may get exchanged with passing stars over eons. You see, other, more recent numerical simulations have suggested that Oort Clouds could exist around other stars too. Our Oort Cloud may also have both an inner and an outer region, each with its own distinct shape. Some scientists suggest that the inner region may be more like a disk, similar to the donut shape of the Kuiper Belt, while the outer region is suggested to form the spherical shell more widely associated with the Oort Cloud. Altogether, the inner edge of this two-region Oort Cloud may be 2,000 astronomical units from the Sun at its closest, with the far edge stretching all the way out into interstellar space, potentially reaching as far as 100,000 astronomical units from the center of our solar system. This means the Oort Cloud could extend more than 1.5 light years across. To put that into perspective, since we're talking about very, very large distances, consider Voyager 2 spacecraft for a moment. as of the publication of this video, Voyager 2 has travelled to a distance of about 139 astronomical units from the Sun since its launch from Earth at 1 AU in August of 1977. That's about 3.3 AU per year, or about 56,000 kilometers per hour. It's the second farthest human-made object in space, just after Voyager 1. In August 2007, Voyager 2 passed beyond the boundary of the heliosphere, the outermost layer of the Sun's atmosphere. It extends out beyond the planets, and 3 times further than the distance to Pluto. Outside of the heliosphere, the Sun's constant flow of charged particles, called the solar wind, is finally impeded by the interstellar medium. And in November 2018, Voyager 2 finally crossed the final layer of solar turbulence called the heliosheath and continued on into interstellar space. Despite passing beyond the heliosphere and well past the main Kuiper Belt, Voyager 2 would still need to travel for another 300 or so years just to reach the innermost edge of the Oort Cloud. That's how far away it is. And to fly through the Oort Cloud, that could take another 30,000 years. Even when traveling at 56,000 kilometers per hour, it still takes all that time just to travel around 1.5 light years. If you've ever wondered why interstellar or intergalactic space travel is difficult, keep in mind that our nearest stellar neighbour is Proxima Centauri at around 4.25 light years away. However, some still question the existence of the Oort Cloud, mainly because we're unable to directly observe it. Another argument has been made that long-period comets may come from other places, such as interstellar space. And in fact, the first observation of an interstellar comet, one that had origins from outside our Sun's influence, was made in 2019 by amateur astronomer Gennady Borisov. Professional astronomers joined in to collect data on comet Borisov, named after its first observer. They found an unusual composition, a higher concentration of carbon monoxide than the average comet originating from our own solar system, suggesting that this comet may have formed in the presence of a red dwarf, a different type of star than our Sun. And yet, the vast majority of astronomers agree that the Oort Cloud is really out there, despite the fact that we've never laid eyes on it. Plenty of indirect observations and mathematical models show great support for the theory, and the evidence continues to add up. But why is it exactly that we've never been able to see the Oort Cloud? After all, with telescopes we can see stars far beyond our own solar system, and even the shapes of distant galaxies. The difference is size and light. Think about it. A piece of Oort Cloud debris is roughly the size of one mountain on Earth. Let's consider Mount Everest at around 9 kilometers tall. Now consider the Oort Cloud's innermost boundary begins somewhere around 3000 AU, or roughly 450 million kilometers from the Sun. The distance from the Sun to the nearest piece of Oort Cloud debris is 50 million times the size of the debris. Talk about looking for a needle in a haystack. But more crucially even, is that stars and galaxies give off light, but Oort debris does not. The planets are relatively close to the Sun, so they are able to reflect the Sun's light and therefore are visible. Likewise, the asteroid belt and even the Kuiper Belt are close enough to the Sun that we can use telescopes to directly observe their debris. But outside of the heliosphere, the Oort Cloud is just too far and too dark for our telescopes to catch a glimpse. Despite the Oort Cloud's gargantuan footprint and pivotal role in shaping our understanding of the origin of many long-period comets, for now, we can still only infer its existence through mathematical models and indirect observation. But don't let our inability to make direct observations discourage you from following the evidence. I can think of a few other times in history when scientists put forth monumental theories despite a lack of direct observation. For example, in the 16th and 17th centuries respectively, Copernicus and Galileo put forth the theory that the planets orbited around the Sun, contradicting a widely held belief at the time that the Earth was the center of the solar universe. Their theory of a heliocentric solar system was not based on direct observation, but rather on indirect observation of the orbit of the planets. As we know, that theory turned out to be spot on. That's the thing I love about science and the pursuit of knowledge. There's always more to learn. The farther we travel through time, the better our understanding of the solar system will get. Who knows? Maybe in 100 years, future astronomers will have found a way to prove the existence of the Oort Cloud once and for all. Or maybe they'll have found a whole new explanation for long-period comets. Until then, the Oort Cloud remains one of astronomy's most compelling enigmas. Thanks for watching. This video was in part made possible by all the astronauts on Patreon. If you think these videos add some educational value to the world and want to give them more stability than the algorithm, you can become a paid member on Patreon to contribute towards their creation. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Just sign up with the link in the description. Once again, a huge thank you from myself and the whole Astrum team.